Okay, so we saw PIT of sparse polynomials, saw PIT of depth through powering, and I want to do now a model which generalizes both of them, so-called read-once oblivious algebraic branching programs, with Ramsad briefly mentioned this morning. I want to dwell on the definition of this, why it's important, and so on. I want to review this Nissan partial derivative matrix lower bound in this context. I want to tell you about white box, then tell you about black box, and hopefully finish in 50 minutes. Okay, so yeah. So I want to first do an example, just trivariate example. Okay, so consider the following directed acyclic graph. Okay, so you're going to have a source S and a sink T. There's going to be 3 layers. Okay, so this is sort of it's a layered thing. I'm going to say that the first layer is X, the second layer is Y, the third layer is Z. And what I'm going to do is I'm going to label every edge in the X layer with univariate polynomials in X. I'm going to label things in the Y layer with univariate polynomials in Y. So here they happen to be linear, but you could imagine something like y squared plus 5. So they don't need to be linear polynomials. They're univariate polynomials in everything. And then here you have something like z squared and z cubed plus z. I don't know why I'm looking at my notes. I just made these up. But this is some computational device. Okay. And I want to say, remind you, why is a computational device? How does this actually compute something? And what is the most general definition? Okay, the way it computes something is as follows. Consider a path from S to T. Okay, this is a direct acyclic graph, so everything goes forward. So what does a path look like? Well, you can start at S, go here, here, and here. That's one path. You could go here, 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 and here, or you could go the top way. So there's 3 different paths. And the point is that every path, I want to say, computes a polynomial because you take a product of everything that occurs on that path. Okay, so for any path P, you can look at the edges E which occur in P. Okay, you look at those edges, they have labels. Take the product of those labels, label it E. Okay, and now I want you to sum over all ST paths. Let's call them P. And I want to say this is your polynomial in 3 variables, x, y, and z, is computed this way. Okay, so that's the definition by example. What are the salient features on a more general setting? Okay, so what's the definition? So it's called a read-once oblivious algebraic branching program. It's a bit of a mouthful. I'm going to call it an ROABP, which is still a mouthful, but I have a big mouth, so I don't know. So what is the definition here, right? So you have a layered direct acyclic graph, right? You have a single source S, you have a single sink T, okay? You're going to have n layers, right? Remember, I have all my polynomials are n variables, right? So each layer will have 1 variable sort of associated to it, right? In this example, I have x, y, and z, right? And then the edges will be labeled with univariates in the appropriate variable. So, okay, so what does that mean? What is the appropriate variable? Well, each edge goes from one layer to the next, right? That layer is associated with a variable. The univariates are in that variable. Okay, and then the width here is the main notion of complexity because there's only n layers, right? So the width is just the maximum number of vertices in a layer. Okay, so that's the main issue of size. Okay, so let's just say, why is this called a read-once oblivious algebraic branching program? A mere defined algebraic branching program is basically computing this way, direct acyclic graphs with 1 source and 1 sink. That's why I'm calling them algebraic branching programs. Why are they oblivious? It's basically because of the fact that every layer has a variable associated with it, right? That you're not reading or using x and y in one layer. You only use, every layer has 1 variable associated with it. And it's read once because every variable occurs at most once. Okay, so that's why it's a read once oblivious algebraic branching program. Bit of a mouthful. Okay. Now there's one subtlety in the definition here, which is what is the sort of the variable order? Okay, in the sense, in this example, right, there's something very weird in the sense that x I artificially made it first, y is second, z is third. So what's going to happen in general is you're going to have some variable order, something like, the most obvious one is this, that x1 is first, x2 is second, up to xn. Okay. I'm going to comment more on the variable order later. But what I want to do now is just state again what Ramprasad said, which is sort of a normal form, which explains why this is computationally simple, which is also Amir said, in the sense that this is a very large summation. Okay, there could be exponentially many ST paths. We don't want to sum over that many paths. Okay, so the dilemma here is that suppose that f of x is computable by a width w read one's ABP. Can I put this in a more computationally nice way in terms of actually computing it? This implies that there exists a1 of x1 up to an of xn, where what are these? These are going to be matrix valued polynomials. So let's parse this for a second once I write it. So these will be the following. Okay. They're going to be matrices whose entries are polynomials. And the point is that A1 will only be a matrix, a W by W matrix, whose univariates depend on x1. An only depends on xn. Okay? And how do these matrices compute F? Well, F will be the 1-1 entry of the matrix product. Right, so this is a matrix product. It's a W by W matrix. You take the 1-1 entry, and that is F. Okay, so if you have with W, they're W by W matrices. And it's sort of, I mean, for me, it's more convenient to think about it this way than the sort of directed acyclic graph, in the sense that working with matrices is something I'm comfortable with. Okay, but I want to comment on what exactly does it mean to have matrix valued polynomials. So there's really two views. Okay, so what is, say, A of x? So one view is sort of the way I put it here, is that you have a W by W matrix, and if this is the ijth entry, what you have here is so ij is a univariate polynomial in X. Right, that's sort of a matrix whose entries are polynomials. But there's an alternate view, which I want to use because it'll be helpful in the algorithmic perspective, is a univariate polynomial whose coefficients are matrices, in the sense that I want to say that f of x of W by W matrices with polynomial entries is the same thing as univariate polynomials whose coefficients are W by W matrices, in the sense that here you can express this as a0 plus a1x plus a2x squared plus up dot 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 to ad x to the d, where each of these AIs, not to be confused with these AIs, are W by W matrices, W by W matrices. Okay, so that's sort of the definition, which hopefully gives you a flavor of what this is supposed to mean. There's like 3 different views. Hopefully one is comfortable for you. And now I just want to talk about this is a variable order thing. Okay, which also gives a nice motivation in terms of why we're studying this. Okay, so if you recall from Ramprasad's talk, right, he showed that like if you have something like a multilinear formula, if you randomly partition the variables into 2 sets, right, then there's sort of this partial derivative matrix is of low rank. So they're saying there's sort of some way to partition the variables, or in particular order them, such that in some sense the correlation between these 2 partitions is low. Okay, so in terms of this variable order, I want to say there's sort of 3 regimes that are of interest here. Let's do the second one first. The second regime is the one I'm going to talk about, which is where the variable order is x1, x2 up to xn. So there's a known and fixed variable order, and every one's ABP will be in that variable order. Okay, so this is sort of the known order case. Okay, the first regime is much simpler, where you will have a polynomial which is computable as a read once ABP in every order. So the read once ABP might depend on the order, but it might be in every order. In particular, it would work for, you have a read once ABP in this order. In the third regime, you have some sort of hidden permutation where it will permute the variables, and maybe you don't know what the permutation is, but there's some order where the polynomial is computable by a read once ABP in that order, but maybe you don't know what it is. And these 3 regimes, it's sort of helpful to recall Ramprasad's talk, right? He had this polynomial product of xi plus yi, right? And he showed that if you separate the x's and the y's, then this partial derivative matrix is of high rank. But if you interleave the x's and y's, then it's of low rank, right? So that's sort of in this second regime here, right? Where there are some some orders where the correlation is large, but there are others maybe where it's small, okay? And basically the point is that if I tell you the order, it's sort of easier to get results, and it's sort of a nice test bed to get things like unknown order. And in that sense, especially with regard to PIT, hopefully then we could say you could do things like approach things like multilinear formulas where in a random partition the correlation is slightly less than maximal. But that's sort of, you know, looking forward 5, 10 years from now. Okay. Yes. So pick an order. So there's some polynomial that we have in mind. You pick an order. I will give you a Re-once ABP in that order that computes that polynomial, and it'll be small.
So one way to achieve this is if it was commutative in the first place.
Right. Right.
But that may not be the case.
It's not super clear how to characterize when it doesn't happen, but that's an interesting question. Okay, so I talked about this, and now I want to comment on the robustness of this model and refer back to this lower bound, this order thing. Okay, so why is this model interesting? It's interesting partly because it has a lot of closure properties. Okay, so small ABPs are closed under the following operation. So one operation is addition. This is sort of stupid, but like if you add two Re-once ABPs in the same variable order, so I'm going to sort of stick in the second regime. If you add two Re-once ABPs in the same variable order, it doesn't increase their size by much. Also by multiplication, if you don't do too many. More interestingly, there's things like taking homogeneous parts. Okay, so you can homogenize Re-once ABPs. You can compute homogeneous parts efficiently. Okay, so this is in contrast to things like depth 3 formulas, right? In the sense that no, I guess you can do that too. But okay, but there's some models where you can't do these things efficiently, and there's also things like. So basically, if you start with W, then you do one of these operations, you'll get something like polynomial in W. Yeah. You can also do things like translate. If you translate your variables, it'll also not increase the width too much. So the point is that, for example, sparse polynomials are not closed under translation, but Re-once ABPs are. And the reason that this is interesting is because small Re-once ABPs simulate the following models. They simulate sparse polynomials. And what does this mean? It means that if your polynomial is sparse, it is computable by a small Re-once ABP. In particular, in every order. Okay? So even though sparse polynomials are not closed under translation, they are contained in Re-once ABPs, which are closed under translation. Depth 3 powering formulas are also computable by small Re-once ABPs, and they're also computable by small Re-once ABPs in every order. And the proof of this was basically given by Ankit, where he showed that this duality trick of Saxena that converts a depth 3 powering formula to a sum of product of univariates. Okay, and that basically gives you the Re-once ABP. So you have F and you have G. They're on the same variables. Suppose that they're computable by width W Re-once ABPs in the same order. Their multiplication should be computable by width W squared. No, there's a fixed order.
No, I'm saying you don't take them syntactically.
Yeah, it's not, you have to think about it. I don't know. Okay, so these two models I already talked about. There's also a nice connection, which I'm not going to dwell too much about, on non-commutative ABPs. Okay, so Ido next week we'll talk a little bit about non-commutative polynomials. Non-commutative polynomials is basically where you have variables you don't assume that they commute. And you can consider algebraic branching programs in non-commuting variables, and there's a very tight connection between non-commutative ABPs and Re-once ABPs, which I'm not going to dwell on, but these are sort of a well-studied and well-motivated class of computation. Okay, so this is the definition. what I want to do now is just review the lower bound technique for this class. Okay, so again, I'm going to use slightly different notation for Ramprasad because I'm not Ramprasad. Okay. Okay, so suppose that you have now a polynomial f. It's going to have I'm going to have a partition. Okay, there's going to be x and there's going to be y, and I'm going to consider it f in the xy partition. Okay. So how do we write this out? Well, keeping with my notation, we're going to sum over a and b. Okay, and a is going to be the exponent vector of x, and b is going to be the exponent vector of y, and then I'm going to have some coefficient alpha. Okay, I'm going to say that the coefficient operator, I'm going to write it in some funky way. Okay, so I want to highlight the fact that this is an xy partition. I'm going to view this polynomial as a polynomial in f y. What does this mean? This means I'm going to view it as a polynomial in y, where the coefficients are polynomials in x. And I want to say this notation is saying I'm taking the coefficient in this ring with respect to y to the b. I'm going to get a polynomial in y. So what is the coefficient of f here? This is going to be summation a over a, alpha ab, x to the a. Okay, so that's just my notation. The space of coefficients in x, so I'm adding a pluralization here, is just the space of all coefficients as you range over all b. Okay, so again, like I'm taking some exponentially large space of polynomials associated with f, and what do we want to do? We want to define some complexity measure. This will be the same complexity measure that Ramprasad gave in this partial derivative matrix. I'm just having a vector space way of viewing it, where mu of f is simply going to be the dimension of the space of coefficients of x in f. Okay, so that's going to be my complexity measure. And it's worth noting that there's a certain symmetry between x and y. Right? I sort of chose x, but you could also say dimension of coefficients with respect to y. It turns out it's symmetric, it's equal, so there's no confusion there. Okay, but the lemma here, basically implicit in the work of Nissan and mentioned by Ramprasad this morning, is that these read once AVPs are small with respect to this measure. Okay, so right, you have f of x, y, and say this is a width w read once AVP. Right, then the measure of f is at most w. Okay, if x comes before y. Right, so there's some variable order. I'm assuming that x comes before y. If that's the case, then the width is at most w. Let's just remind you why this is true. Right, so f is going to be the product of ai xi times the product of bj yj, and then you take the 1 1 entry. Okay, so this is a matrix product in the x's. Let's assume I'm ordering the matrix product, so the first variable comes first, second variable comes second, and so on. And I'm ordering this matrix product accordingly. But because x comes before y, again, x becomes before y in the product. And then the basic point is that if you take a coefficient in y to the b with respect to f, this is simply going to be some scalar times, well, let's not do it that way. What you can do is you can, if you have a product like this, these are matrices, each of which are small. Right? Each of these are w by w. What I want to do is because I'm taking the 1 1 entry of this matrix product, you can actually express it in the following way. You can get gi of x times hi of y. And I will run from 1 to w. Right? Because if you take two matrices and you take their 1 1 product, 1 1 entry, you're only really looking at this first row times this first column. Right? So I can reduce a matrix product of the 1 1 entry of the matrix product to an inner product of the two things here. Okay? And then if you take a coefficient, the y to the b coefficient of this thing, it's gi. Right? If you take a coefficient of this thing, of this inner product, this gi of x is sort of a scalar from the field. So this will be the summation of gi of x times the coefficient of y to the b in hi of y. So you take a coefficient, you get a summation of the gi's times coefficients here. This thing will be a scalar in your field. Okay, so you have this variable disjoint inner product. You take a coefficient with respect to the y's. You get a linear product of variables of polynomials in x. But how many polynomials are there here? This is I from 1 to w. Okay, so this is contained in the span of g1 of x up to gw of x. Right, and this is w dimensional. Okay. Right. Okay. So this is saying that in this particular variable order, you have low complexity, right? And basically, the dimension, or the mu, of this product xi plus yi, this is basically the rank of the partial derivative matrix. Because you're doing x before y, this will be 2 to the n, if this is a product of n variables. Okay, so this is basically saying that in the x before y partition, this is large, while any read once ABP is small, and that's why you get your lower bound. Okay, so that's just reviewing in this language, saying that we know lower bounds. Okay, great. Okay, so I'd really like to say that if we stare long enough at this lower bound, and our eyes water with pain, we would actually get hitting sets or something. It's unfortunately not that easy, so we actually need to do real work. Okay. So what I want to do now is sketch this theorem to you of Raz-Shpilka, saying that there is a polynomial time white box PIT deterministic for read-once AVPs. Okay, and I'm going to phrase it in a way which is amenable to going to the black box case. It's not necessarily originally phrased this way. Okay, but the idea here is as follows. Let's go back to this definition. Right, we have a product of matrices. Okay, and the thing about this product is that it's variable disjoint. So what we really want to do is we want to cut this product in half. Right, and the point is that based on this lower bound technique of looking at the dimension of coefficients, if we cut it in half, the amount of communication between the left half and the right half is small. So what we want to do is we want to cut in half, sort of recurse on each half, using the fact that they're variables joint, and then combine. Okay. Right, so we want to exploit variable disjointness. The challenge is that what do we, like, we're going to split in half. I'm going to give one half to Amir, the other half to Ramprasad. I want Ramprasad to do something, get back to me. I want Amir to do something, get back to me. And then I will combine that information and decide whether this computation is 0 or not. The challenge is what is Ramprasad and Amir, what are they going to tell me? Because they can't really communicate in this game. The challenge is that if Ramprasad just said, you gave me a subcomputation of this thing, and the subcomputation is non-zero, well, that doesn't really help me. I need more information. I need like a strong induction hypothesis. So basically what I want to do is I want to cut this thing in half and get a good amount of information, but not too much, sort of like a Goldilocks thing here. Okay. And so what am I going to sort of remember about these subcomputations? So I want to define a notion that I'm calling coefficient span. Will be the span of coefficients, which will be reasonably clear. But let's go through the definition. Okay. F of x, capital F of x, I'm going to leave the land of polynomials. I'm going to stick with matrix-valued polynomials. Okay, so f of x is going to be a matrix-valued polynomial, and here it is going to be multivariate. Okay, well, what does that mean? It's a summation of monomials times coefficients, and these coefficients are w by w matrices. Okay, so this polynomial is non-zero if and only if all of the coefficients, it's 0 if and only if all of the coefficients are 0. I want to have a more refined notion. That refined notion is the observation that this space here is a vector space. It's a vector space of dimension w squared. Okay, so the coefficient span of this matrix polynomial f of x is going to be defined as the span of these f sub a's. Okay, right? These are matrices. I'm thinking of them as w squared dimensional vectors. There's exponentially many of them. You take their span. That's some vector space. That is the coefficient span, right? It has some dimension. Dimension is somewhere between 0 and w squared. Okay. And the reason I'm interested in this is what I want to say is that in the PRT algorithm, I'm going to cut the computation in two, give half to Ramprasad, half to Amir. They're going to come back to me with the coefficient span. And I want to say that if they tell me the coefficient spans individually, I can combine them in a way to do the recursion well. To motivate that more formally, let me just give a sequence of lemmas. Suppose the polynomial is 0. Then that means that all the coefficients are 0. I want to say that would imply that the coefficient span is 0. And this is an if and only if, right? So the coefficient span of f, it's some subspace. And that subspace is 0 if and only if all the coefficients are 0. Right? That's sort of like an easy thing. But this is saying basically that I really want to preserve non-zeroness, and I'm generalizing that by looking at coefficient span. That coefficient span determines non-zeroness. Okay. So here's like the key lemma that kind of powers the main thing, which exploits this variable disjointness. Okay, so suppose now you have two matrix valued polynomials. Okay, these are w by w, and these are going to be variable disjoint. Okay, and suppose I give A to Ramprasad and B to Amir, and then they come back to me and they give me some other matrix valued polynomial. Okay, so here we're going to have A prime of x prime and B prime of y prime. They're also going to be w by w and variable disjoint. Okay, so all these variables are disjoint if they're not otherwise obviously equal. Okay, and what's the hypothesis that I want from this conversation? I want that the coefficient span of A of x is equal to the coefficient span of A prime of x prime. Okay, so suppose this is true, and suppose the same thing is true for B of y and B prime of y prime. Okay, the conclusion here is that implies that the coefficient span of A of x times B of y is equal to the coefficient span of A prime x prime times B prime y prime. Okay, so what this is saying is Re-once ABP is a product of variable disjoint matrices. I give half to one player, half to the other player. If they come back to me with matrices A prime and B prime, which happen to have the same coefficient span, then I have preserved the overall coefficient span of the entire polynomial. Okay. So let me attempt to fumble. Sorry. What does this mean?
No, what did they explain?
X prime are just new variables. So I made up some new variables, bought them at the store, and so I have a new polynomial in new variables. Okay, so let me. Okay, so let me start with giving an example, and then you can ask your question again, and hopefully between the two of that, it'll help. Okay, so suppose that A of x, xy, is going to be equal to 0, 1, 0, 0, plus 1, 1, 0, x, plus 1, 1, 0, 0, y. Okay, so suppose you have a polynomial like this, right? There are three coefficients, and this is probably a terrible example. Let's give minus 1, 0. Okay, so there are three coefficients here. They're all 2 by 2 matrices, right? So naively, the amount of information in here is sort of like three matrices, but the point is that this is actually a two-dimensional set, right? So the coefficient span of A is equal to, hopefully, the span of the two matrices defined like this, right? And so the whole point here is I'm compressing the many, many monomials I have here to their basis. Okay? And what I'm going to do here is imagine now an a prime of x prime. What I'm going to do is I'm going to take these two coefficients, I'm just going to bundle them into a new polynomial that I just made up. So imagine the following polynomial like this, where I take this coefficient, it's the constant term, I take this coefficient, it's the linear term of x prime. Okay, I want to claim that the coefficient span of a of xy is equal to the coefficient span of a prime on x prime. I mean, this is sort of obvious by definition, right? But the beauty of this whole point is that this is a vector space, right? What is its dimension? Its dimension is at most w squared. Okay, but this polynomial, or if I had more variables, could have exponentially many monomials. And so what I'm doing is I could take this exponentially large set, and I could just prune it to a basis, and I could still preserve the coefficient span, and I could use many fewer variables. Okay, so the lemma here, so I'll get to that proof in a minute, but suppose you have something like this. You have a of x. This is a w by w matrix. What I want to do is I want to map it to an a prime on x prime. So this is many variables. This is a single variable. This will be of degree, again, degree at most d, say, and n variables. This will be degree w squared. So I'm going to have a lemma. It's algorithmic. You give me this. I'm going to give you this, where the coefficient span of a of x is equal to the coefficient span of a prime x prime. X prime is a single variable. Okay. And I can do this in polynomial in what time? You have n plus d choose d and w. Those are the two parameters. Okay. And what is the proof of this? You basically look at all coefficients in A, right? How many of them are there? There's n plus d choose d of them. Okay. Find a basis. How do you find a basis? You know, it's a bunch of vectors. Use Gauss elimination, find a basis. Okay. And then, how many elements are you going to have here? Right? This is a vector space. Its dimension is most w squared. There's at most w squared many matrix like coefficients here. Okay. And then pack these coefficients into a prime. In the same way that I pack these coefficients into this a prime. Doesn't really matter how you do it, you just place them there. And because of that, the coefficients of a prime are exactly the basis of this space, so the coefficient spans are the same. So is this reasonably clear? I mean, yeah. Right. As Natty's saying, you know, you give me an a prime, or a, whatever it is, I'm going to give you back an a prime. It's efficiently computable and has this preservation of coefficient span. Okay. So this is saying that you can take a Reed-Wentz ABP and you can compress it into a univariate polynomial with the same coefficient span, and the price that you pay is n plus d choose d, which is terrible if n is large. Okay? And so since it's terrible, we won't do it when n is large. I mean, what else can you do? But I want to go back to this, and because this is what's going to allow us to avoid the n large case. Okay, so what's the proof of this? So proof of thingy. No, this is, okay. So suppose you have A and B, and suppose you have A prime and B prime, such that you have this, then the coefficient span of A times B is the coefficient span of A prime times B prime. Okay, so how do we prove this? Well, I'm doing this online because I wasn't planning on doing it. But so suppose you have A of x, right? This summation, something like this, right? And suppose it has basis, A1 up to AW squared. Or it has a, maybe not a basis, but like a spanning set. Right, because this is W squared dimensional, so we can always find a spanning set of at most W squared things. Right? B of x is the same thing with B sub B, x to the B, y to the B. Right, and we have B1 up to BW squared. Okay. And let's just not prove that in full generality for the moment, but prove it in the way it's going to be used, which is here. Okay. I want to say that the coefficient span of AX times BY is equal to the span of AI times BJ as you range over all I and j. Okay. So right, the coefficient span of A is equal to this. The span of these things. The coefficient span of these things is equal to here. I want to say when you take the product of these polynomials, it's equal to the span of the products of the bases. Okay. This is basically because matrix product is bilinear. Okay. And the point is that what is this thing? This is equal to the span is equal to the coefficient span of summation AI x to the x prime to the I times summation bj y prime to the j. Right? Because the coefficients of this product are exactly these matrices. Okay, so what I did is I took these these two matrix valued polynomials, I distilled their coefficient span, and I repacked them into smaller things. And because of bilinearity, I haven't changed the coefficient span at all. And this is really using variable disjointness, like a lot, right? Okay. Okay, so those are the two key lemmas. And what I want to do now is say, how do we actually get this algorithm? Basically, we're going to do what I already said, is that we're going to do a divide and conquer. And so let me just give you the proof idea when we have 4 variables, because that basically has the main ideas of the proof. Okay, so suppose that you have f of x, y, z, and w. And this is a of x, b of y, c of z, d of w. Okay, so this is a Re1 CVP on 4 variables, and if you took the one entry, you get like a genuine Re1 CVP. We want to compute the coefficient span of this thing. The point is that we have two things here, okay? And what we can do is we can say this product, if we take the coefficient span, like we can compute basically by what I did here, this thing, right? We're going to use this when n equals 2. Okay, we take two variables at a time, and we can compute here an x prime, a prime x prime, where the coefficient span of a prime x prime is equal to the coefficient span of a times b. Where basically what we're doing is we're opening up a, we're opening up b. If this is degree d, this is degree d, there's d plus 1 coefficients in each. There's d plus 1 squared things. That's the complexity here. This is d plus 1 squared. Many matrices. We compress it down to w squared, because that's the dimension bound. So this is now w squared degree. We can look at these two matrices. We can do the same thing. We get c prime of z prime, where again the coefficient span is the same. They're both going to be polynomial time reductions, right? And this key lemma here that I stated here, this lemma is saying that we can independently preserve coefficient span, and the whole coefficient span is the same, right? So these two things have the same coefficient span, written in terrible handwriting. Okay, and then what you do is you just recurse and say now you have, again, two variables, right? So now you get an a double prime, x double prime, where the coefficient span is the same. This is of degree w squared. And now you have a polynomial, a matrix value polynomial in w squared entries. And what you want to know is, what is the sort of 1, 1 entry? And you basically can just look at all of the w squared matrices, and you're done. Okay, so the lemma, the final lemma is, how do you deal with the one variable case? It's just that if a of x 1, 1 is equal to 0, if and only if all, so suppose that this is summation ai xi, if all ai 1, 1 are 0. Okay, so if you have a univariate, you just look at all the coefficients. All of the 1, 1 entries 0. Okay, so this is a process that recursively gets you down to a single variable, preserving all the coefficient span. You look at this last lemma, and again, you can then read off whether the polynomial is 0 or not. Okay?
Why do you do it by reduction? Why not just do it simply level by level? Or does it give you next something?
Sorry, when you say reduction, like the fact that I'm doing it in parallel? Or
Just take half and half. Why not just from the top to the bottom?
like, sorry, you're saying like merge x and y, and then with z, and then with w?
Well, in this case, it's like a simple case because there's only 4 layers. But if you do it like you said you're doing by recursion, you start from.
So I'm building, okay. So maybe this is your question. Okay, so I'm doing a binary tree. And the question is why? Right, you could do, like this is doing a binary tree like this. Right, you could imagine where you you merge the first two, and then you merge something like this, and then something like this. So, no, so this will work. So this will work. Yeah, so Raz-Shpilka, yeah, so in their paper, they write it this way. Okay, the reason I'm doing this way is for 2 reasons. Okay, so one is that this will give you a polynomial time algorithm. If you do it in a binary tree, this will give you an NC algorithm. Okay, and okay, what's that between friends? I don't know, but like, this is actually important for my next thing, which I'll talk about in 5 minutes, which is black box PIT. Okay, so the distinction between these 2 cases is not super important, but it is really important that I'm doing this in logarithmically many rounds for the next thing. Okay, so, all right. So here's the question. Why is Raz-Shpilka a white box? Okay, like what do we know now that Amir and Ron didn't know 10 years ago? NC2. Well, it's NC2 because you have to do linear algebra. I think it's actually, is it NC3? I think it's NC3. Well, I don't remember. It's either at most 3. Okay, so why is this white box? And I want to say that the main reason it's white box is because of this lemma. Okay, I want to say that this lemma is not compatible with evaluation access only. Because what are you doing? I'm giving you a polynomial. I am explicitly looking at its coefficients, and I am repacking them using Gauss elimination into something smaller. Okay, I'm not evaluating this polynomial in any way. I'm really, really looking at its coefficients. And so that's really, really white box. Okay, and so the answer here is Gauss elimination. That is entirely the reason why. And so what you really need to do is do a black box version of Gauss elimination. Or more philosophically, how do you row reduce a matrix without seeing it? Right, so this sounds like some sort of Zen puzzle, which I'll solve for you now. Okay. So, and so I mean, then sort of, how do you do this, how do you do this black box? The answer is basically that you can't do Gauss elimination black box deterministically. That's just not really possible in whatever that even really means. Basically, what we're going to do is we're going to do, Gauss elimination. We're going to do this with randomness. Okay, so let me just give you the simplest version of what I mean by Gauss elimination and how you solve this with randomness. So what is Gauss elimination? Suppose you have a matrix like this, it's tall and skinny. There are n rows and r columns. Okay, what does Gauss elimination do? Look at the rows of this. Clearly, they're most r-dimensional, right? But there are n of them. What can Gauss elimination do for you, right? Or what can you do for Gauss elimination? I don't know. But like, basically, what you can do is you can pick out r different rows, and you can get an r by r matrix. So this is m, and this is m sub s. So S is some subset of n of size r, where you've picked out a spanning set, right? So here the row span of m is equal to the row span of m restricted to S. That is what Gauss elimination is doing for you. And if you notice, that's all we needed here. We don't need a basis. We just need a spanning set which is reasonably small. Okay? And so what I want to do is I want to get the same phenomenon without actually looking at it in any way. Okay, so here's the observation. Suppose you do the following. You have your matrix M, and then you multiply it by some E. Okay? What you're going to get is you're going to get some EM, and let's say this is R by R. Okay? What I want to say is that when is the row span of E times M the same as the row span of M? Well, the first observation is suppose you pick E at random. If you pick E at random, then it's not too hard to show that the row span is the same. Okay? So if E is random, then the row span of M is equal to the row span of EM with high probability. Okay? Now, so what we want to do basically is instead of doing Gauss elimination computationally, we want to replace it with a random matrix like this. Okay? And that's why we want to do this in parallel. Because we're going to spend some randomness, but we don't want to do it, we don't want to spend too much randomness. So at every level, we're going to use one amount of randomness per level, and because we can use union bound or something. And the number of times we do it is we want to make that small. So if we did a sequential algorithm, we would have many, many levels of using randomness like this, and that would be bad. Okay, so the key definition here is something called a rank condenser. Because I said here we use a random matrix, but how many random bits am I using? Well, this is an R by N matrix. Okay, that's a lot of random bits. That's way too many. I don't get paid that much. Right? So a rank condenser is a collection of matrices E of R by N such that for all M, there exists an E in curly E such that the rank of M is equal to the rank of E times M. And this condition here is equivalent to saying that the row span of M is equal to the row span of EM. Okay, so basically the amount of randomness used in this process corresponds to the size of our rank condenser. Okay, and the main theorem here is that there are explicit rank condensers. Sorry, I didn't quantify over M. So for every M, this is going to be N by R matrix, M's of this form. There's an explicit rank condenser where the size of E is at most polynomial in R and N. Okay, if you just took a random matrix, that would give you an exponentially large collection of matrices, which is too much. But here, you need to pick a random element from this set, which is sort of like logarithmically many bits. So this is much more randomness efficient. And so basically what you do is the theorem here, doing myself in a mirror, is there's a polynomial to the log n, this is NSD, size hitting set for V1's AVPs in this known order scenario. And basically what you do is you use this Raz-Shpilka paradigm where you're sort of compressing coefficient span, but you replace Gauss elimination with a rank condenser. Now, unfortunately, there's a number of more details because obviously I didn't tell you how to get this rank condenser. This rank condenser also needs to be compatible with black box access. This kind of goes back to the sparse polynomial thing, where I needed not just some map that has no collisions, but a map that's compatible with the fact I'm only giving you evaluation access. You can do that. I mean, the most natural rank condensers have this property anyways. And then the point is that you only use polynomial in R n sort of guesses sort of per round. Okay, right? You're doing, in this example, right, you do Gauss elimination here, you do Gauss elimination here. Because they're independent, you can basically use the same rank condenser for both using a union bound. Okay, so you only need to sort of use a small amount of randomness in every step. And then you have sort of log n steps. And so this gives you polynomial to log. Okay, so that's the, just to review. So we defined Rewin's ABPs and several boards ago. I told you about the lower bound techniques. It's very much related to partial derivative matrix and non-commutative APs and so on. Viewing these Rewin's ABPs as variable disjoint gives you this way to partition them into two different subcomputations. Preserve coefficient span, you can recombine them using Gauss elimination and so on, and you can do this process iteratively using the fact that you can do this in parallel, and using these rank condensers, then you can transform it into black box. Okay, thank you.